Animals communicate with each other in a lot of different ways, using vivid colors, dances, sounds, odors, or even electrical signals. And these signals are often quite conspicuous, striking, and beautiful. So today I'm going to show you a lot of visual examples because they're the easiest to show in photographs, but keep that diversity of signals in mind. So I'm an animal behaviorist, and I'm particularly interested in acoustic communication or communication by sound. Animals often produce characteristic sounds, calls, or songs that serve important functions, like attracting mates. And these sounds are so conspicuous and captivating that they're often one of the first things that we teach our children about the natural world. But why animals make conspicuous signals famously posed a frustrating puzzle for Charles Darwin, who wondered why signals like a peacock's tail could ever evolve, since they seem so costly and dangerous to produce. And the answer to that evolutionary puzzle is basically that if signals are useful enough at attracting prospective mates, then they're worth the cost. Over the years, we've unraveled a lot about what these signals communicate and how and why receivers extract information from the signals. In a lot of species, like in these peacock spiders, males produce signals to advertise themselves to prospective mates, and females use those signals to make mating decisions. Signals can encode information about a male's quality. Is he strong? Is he fast? Is he agile? Does he have a lot of energy to spare? And does he bear good genes? These male widowbirds are producing multiple signals. Females are judging them based on their tail length, jumping height, and most importantly for this talk, their jumping rate. And females have really definite standards. But how do we know what the signals are that receivers prefer? We can't really ask them, but we can turn the natural behavior of an animal into a sort of a survey. For instance, some animals, like the tree frogs we study, move towards sounds that they think are calls. They move faster towards signals they think are attractive, and if given more than one choice, they move toward their favorite. And these simple tests have been used to great effect to understand the evolution of signals. Males with attractive calls are better dads. Their babies survive better and develop faster, which is important because just about anything will try to eat an awkward, still developing young tree frog like this one. So females that choose good calls are rewarded with fitter offspring. But the world is a really noisy place, and choosing the best call isn't always easy. In my lab, we're inordinately fond of noise. And you might think you already know what noise is, but if you had to define it technically, you might stumble. So broadly, we can define noise as anything that interferes with signal detection or discrimination. And note that noise is not always a sound. The first kind of noise I'm going to talk about is pretty intuitive. It's the sound of a chorus, or all of the signalers that have gathered in the same place at the same time to produce signals. This is a single male gray tree frog. It might be familiar to you. They're local here in East Tennessee. But in the real world, a female tree frog has to hear that male, judge how attractive he is, and then find him in the dark against a backdrop that sounds a lot more like this. Receivers find that really difficult. In loud chorus noise, they make mistakes, choosing males they would never ever choose in quiet. And these mistakes can have really disastrous consequences. For example, I photographed this female toad accidentally mating with a male tree frog in South Knox this summer. That's a pretty big mistake. A second, more abstract kind of noise is inconsistency in signaling. Males call repeatedly, but they don't call the same way every time. It's a bit like if you had to judge a high jump competition not only on the maximum height jumped by each athlete, but instead on the average height of all their jumps over a period of time. Some individuals are consistent and others are not. In the tree frogs, males call repeatedly and females pay attention to that rate of calling. They prefer high call rates and they care more about that than they care about most other things. But look at this male calling over a span of 3 minutes. The dash line is his mean, and he's wavering all over the place. Sometimes he's much faster than his average. Sometimes he's much slower than his average. And we hypothesize that this kind of noise could make it hard for females to know what the truth is. She listens on average for only about 2 minutes, and the length of the colored windows is 2 minutes. But which 2 minutes? A listener could come to wildly different conclusions if she sampled the blue windows versus the red one. So does that kind of variation impact female decisions? Yes. As inconsistency increases toward the front of the plot, female choices, which are the colored surface for fast call rates, deviate from their choices when the signals are perfectly consistent. That's the gray surface. And inconsistent males are clearly now getting away with something. But the information conveyed by the signals is important to receivers, right? So if inconsistency is hiding that information, we might expect females to pay attention to the inconsistency itself. So we gave females choices between calls that differed in inconsistency but were otherwise identical, and they strongly preferred not to mate with the inconsistent males. Okay, so we show that in one sense, this inconsistency in male behavior is noise, because remember, we defined noise before as anything that interferes with signal detection or discrimination. We also showed that it's not entirely noise, in the sense that receivers do care about it. They are paying attention to consistency. So we're currently laying the groundwork to think about whether these ideas are true in a much broader sense than in this one tree frog species, and we can test that by looking at independent lineages that evolve signaling and even ears independently. For instance, in animals as distantly related as these Australian field crickets and these gray tree frogs that live in Tennessee. And ultimately, I think this idea is a really big one. So any signaling that's repeated through time is susceptible to this idea of inconsistency as noise. So this is important not just for frogs and crickets, but for the widow birds and the peacock spiders. And zooming out even further, this question is not really about sex specifically, and it's not even about animals in general, because communication is one of the biggest ideas in the world. It applies to two cells signaling to each other in your body. It applies to two satellites communicating to each other in orbit, and the increasingly huge number of speech interactions between humans and machines. And everywhere you look, there's noise. Thanks.